Okay, so today we will start discussing path integral formulation of quantum mechanics. Path integral formulation of quantum mechanics. So let me begin with motivation. Recall that um, the usual Schrodinger theory, you write the Schrodinger equation I h bar ddt of psi t is equal to h acting on psi t being the state vector, h the Hamiltonian. And there the goal is to find the time evolution, which means that given the state vector at some initial time, say ti, find the same at a final time, say tf. Now, this is intrinsically non-relativistic because time is obviously playing explicitly playing a special role. So time playing a special role. So the question that one would be interested in, what is the relativistic generalization of this? Now, in this context, Dirac had a proposal which we will be considering here in our discussion. So Dirac said that the way the problem is being formulated itself is problematic, because the way you are asking the question, there itself time is playing a special role, and therefore that does not fit a relativistic formulation. So one should have a formulation where both space and time, even while asking a question, both space and time should play and should be on an equal footing. So his approach is look for a formulation where both space and time are on equal footing. Now, the similar situation can also be observed in classical mechanics. The difference between classical mechanics and quantum mechanics is in the way how mechanics works. For example, in Schrodinger theory, you are writing a Schrodinger equation, and in classical mechanics, we'll be writing a classical equation of motion. But the more basic, at a more basic level, they are basically the same. Both of them are mechanical problems, and there also you can see this in classical mechanics. There are two ways of doing it. One is Hamiltonian framework, where one is given a Hamiltonian that describes the system, and that Hamiltonian, using this Hamiltonian, you find the time evolution of the system. That the time evolution is a classical equation. In quantum mechanics, that is the Schrodinger equation. But nonetheless, these two are similar. So this is analogous to the Schrodinger theory. And there is another alternative approach, which is Lagrangian framework. There, the basic object that you consider, the theory is described by what is called an action. And this action is a functional. We will see what that means in a while. The difference between the new thing that and the new feature that in this action formulation or the Lagrangian formulation is that you talk about trajectory in an extended configuration space. An extended configuration space is nothing but time added to the configuration space. So, for example, if you have 1 degree of freedom, so you have time and then space x and t, and the motion of a particle will be given by some trajectory like that, x, which you could describe as a function like x of t. Now, if you give some initial and final conditions, say initial condition time ti and x at ti, and then x at tf is a final point, then you could ask the question, what is the right trajectory through which the particle will move? Okay, and action functional is given by action x of t. Let me not put t here. I will explain the notation. X is equal to dt, integral dt ti to tf, and then Lagrangian x dot and t. When you do this integral, you have to know x as a function of t in order to calculate the Lagrangian at a particular time, and then you integrate that function of time from t1 to t2, ti to tf. But in order to do so, you have to know what the function x of t is doing at ti and tf. So these are boundaries. So there are some boundary conditions. Boundary conditions is that x at ti, say some given value xi, and x at tf is some another given value xf. So this corresponds to, this is xi and this is xf, right? And this is ti and this is tf. So now you see, so when I write the square bracket x within the square bracket, then x does not refer to a real number, but x refers to an entire function x of t. This is an entire path from the initial and the final point, from the initial points to the point to the final point. So that's the meaning of this square bracket, meaning of this notation. And action is not a function, rather it's a functional, because as input it is not taking a real number but the entire path, and giving out a real number. So if you want to compare these two, a function versus a functional, a function, say fx, it takes a real line to a real line. So if you draw a curve, you can draw a curve like this, fx versus x square. So what goes in the as an input is a point on the real line. Okay, so usually it is called the domain on which the function is acting. The domain is the real line, which is this one. Okay, and of course, if it's a real function, then also its value is a real number. However, the crucial point to note here is the domain is a real line, and the specific value of the argument corresponds to a specific point on that space, that is the real line. However, for a functional, s of s square bracket x, it is not it is not a mapping from R to R. Rather, it's a mapping from a more complicated space to R, and that more complicated space is, let me call it curly F to R, where this curly F is a space of functions. Okay, so as I was explaining, you have to first look at, so this x in the square bracket is not a real number, rather a path connecting two endpoints. Okay, so this one, so this is ti, xi, tf, xf. Okay, now that space is infinite dimensional. So let us try to have an idea of what that means, and a more abstract way of looking at it. But nonetheless, it's geometrical, so it's not a big difficulty to do that. So suppose, so since I was saying earlier that x here, when you write a round bracket, x is a real number, which means x is a point in a space which is a real line. Here, when x is in a curly bracket, is in a square bracket, then x is a path, and then that x belongs to another space f, that space of functions. And just like we had this real line over here, we are trying to. This is very easy for us to understand what this space is, but we are trying to have an understanding of what this space is, curly f. So let us try to draw. So suppose it's a cartoon. This is that space. And I already said it is infinite dimensional. We'll see why. Okay. So in that space, just like here, in this case, real line, given one particular value of x, is same as giving a particular point in that space in the domain, right? Here, given one particular value of x, should also be same as giving one particular point in that space, f curly f. However, that point is not a real number, but the entire path. So this x here, so let me put this x as a square bracket. So this x within square bracket it corresponds to this entire path. Now, what is the dimensionality of a space? Dimensionality of space tells you how many independent directions you could move the original point to. So this is your point, this is your original point. In how many independent directions could you move? So on this piece, on this flat surface, we of course have two independent directions because it's a two-dimensional space, but we are trying to imagine that it can be larger. For example, in case of 3 dimension, we draw a thing like this. This is with a perspective, we can imagine that it's a 3-dimensional space. For 4 dimension, we cannot imagine, but we can be a little more abstract to probe this question. The more abstract question that you can ask is it's a number of ways, it's a number of directions, independent directions, or the number of independent directions in which this point can move. And this point moving means this function is changing, because this point represents this function or the path. So you could ask the question, in how many ways could I modify this path? And there are infinite number of ways, because at each point you could make a change, and at each point, and that will be an independent change. As a result, you will be able to get these are the neighboring paths. So those neighboring paths, if you wanted to classify how they are different, they can differ from the original path in infinite number of ways, because at each point you have a degree of freedom of modifying the curve. Okay, so therefore there should be infinite number of independent directions along which the point could move, right? So the picture that I'm trying to give is that one specific path, one specific function x of t is represented by a point here, and the neighboring paths with the same boundary conditions will be given by neighboring points around that point. Okay, and since there are infinite number of independent directions you could go, it's an infinite dimensional space. Okay, so I hope this concept of functional is clear now. So whatever we were doing about functions in this real line case, you are basically considering a function on f, and that's a functional. Okay, because when you refer to this argument x, that doesn't actually refer to a point. That is not a description of a point in f. It is by the square bracket you tell people that this corresponds to the argument is of entire path, which is a point in f. Okay, so so question would be then, since in this way of describing the mechanics, you are only considering paths in an extended configuration space, both space and time seem to be treated on an equal footing. Question is that could we have a reformulation of quantum mechanics in terms of action?